This is section 3.2, polynomial functions and their graphs. In 3.1, we talked about the graphs of quadratic functions. Those were equations that started off with an x squared. Now we're going to take what we learned there and we're going to extend it to a general polynomial. Now here's the definition of a general polynomial, and it looks awful, I know that, okay? First of all, remember that the degree of a polynomial is the largest exponent that appears. And right here, I've got these written in descending power order. So if this is 5, 5 minus 1 is 4, then you can have 3, 2, 1, and then a constant. Or technically what's happening here is this is x to the first power and this is x to the 0 power, okay? Notice that the way these are written, the coefficient, the sub number that goes on the coefficient correlates with the exponent. So if this is a fifth power, this would be a5. Here's a2 and a square, a1 and the understood first power, and a0, which is often read a naught. Naught is an old word for 0, and for some reason it's stuck in problems like this. So a naught x to the 0 power. And remember that anything to the 0 power is 1. So this all makes some sense. We need to know how to tell the degree. So we would look at our polynomial. And this is a polynomial where everything is all multiplied out and like terms are gathered. Whatever the largest exponent is, that's our degree. And if we can identify the degree, we can know a lot about what our graph is going to look like. And again, I know you're going to be getting using graphing calculators eventually. These are just things that you can recognize usually from the very beginning and have a good idea of what your graph is going to look like. So you can catch those kinds of mistakes where you just enter something wrong. Okay, so the a sub n, which is the number in front of our x to the largest exponent. So if we have these written in descending power order, an is our first coefficient. This is called the leading coefficient. Okay. The graph of a polynomial function is smooth and continuous. Now these have very specific meanings in math, but in general, what smooth means is you don't come to sharp points anywhere. And continuous means that you don't have any jumps. Okay, so a polynomial function, whatever it looks like, it's going to be a smooth curve of some kind. Okay? All right, so this is called the leading coefficient test. Okay? And it's going to give us a very good idea of what our general shape of our graph looks like. Now you notice on these graphs you have some dotted areas in the middle. Okay? And that's because a lot of things can happen in that central area. We'll get to all of that in a minute. But the leading coefficient can tell us whether our graph starts in the bottom left and goes up to the upper right, or any of these combinations. It can tell us where our endpoints go. Now notice right here, for n odd, so this means we have odd degree. So our largest exponent is some odd number. Okay, if we have some sort of odd degree, then our graphs are going to be going in opposite directions on the ends. Okay, now if the number is positive, then our graph looks like this. Now again, things in the middle can happen, crazy things can happen in there. But if I have 3x to the fifth as my first term, then my graph is going to be starting in the bottom left, goes up to the right, and because this is a positive number. Now, if that number is a negative, it flips upside down. Now, what you might remember from the last chapter, when we were talking about transformations of functions, we had what we called the general cubic, which looked like this. And this would be something with odd degree, and you can see that it does match that general idea. And we learned that this was our basic cubic, okay? But if the number was in front, that was a reflection about the x-axis, right? Which flips it like this. So if you can remember what happens with a cubic whenever we do transformations from the last chapter, you can remember that odd degrees look like this when the number in front is positive and look like this when the number in front is negative. Okay, now if we have an even degree, This would be like what we did in the last section where we have a square. Okay, so if we have an even degree, then if our number in front is a positive number, both ends point up. This is analogous to what we did where we said it opens up. Okay, and then if the number in front is negative, it opens down. And again, if you think about the transformations, we talked about a general quadratic, and then if the number in front was negative, we flipped it over the x-axis and we got this. Okay? All right. One more little thing here. Okay, you notice how these things can have squiggles in the middle? Every time it changes directions, so there and there, or here, 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 and here, every time it changes directions, those are called turning points. And we're going to get to those in just a second, but we will be able to look at our function and know the maximum number of times it's allowed to turn. We'll get there in a minute. Okay. Now, in order to get a graph of a polynomial function, we must find its zeros, okay? Another word for zeros are roots, okay? So what we mean by that is we must find the x-intercepts. To find the zeros, this is another way of saying where do we cross the x-axis? Where is this thing equal to 0, okay? And the graph of the polynomial will either cross the x-axis at an intercept, or it will touch the axis and turn around at that point. So like right here, we cross right here, okay? But it is also possible that we have some sort of graph, and then when we get to 0, we just turn around real quick. We don't actually cross it, we touch it and go back up, okay? And again, once we're going to be able to tell whether we touch, like right here at a 0, or if we cross, like right here at a 0. The way we tell that is by thinking about the multiplicity, okay? We talked about, in the past, when we talked about solving quadratics, we talked about the possibility that you get the same answer twice, okay? If you get the same answer twice, then what we say is that it had multiplicity 2. All right, so multiplicity is the number of times you get that 0. If you get it twice, it's multiplicity 2. If you get it 4 times, it's multiplicity 4. If you just get it once, it's multiplicity of 1. If you get the 0 an even number of times, then you're going to touch and then turn around. If you have a 0 that is an odd multiplicity, then you're going to cross at that point. Okay? So let's look at an example problem. We want to find the zeros, the multiplicity, and whether the graph touches or crosses at each 0. Okay, let's look at this first, and I want to show you how to find the degree of something like this, where the things are not multiplied all the way out. Okay? What you want to think about, and it's actually pretty easy to do, if I were to multiply this whole thing out, I don't have to worry about the details of it, but I know that if I multiply this out, my largest exponent on just this piece, when I multiply it out, that's going to be an x squared. That's going to be my largest coefficient there, my largest exponent there. And if I multiply this out, x minus 4 times itself 3 times, I'm going to end up with an x cubed in it. Okay, and that's going to be my largest exponent in this one. And then when I go to multiply these together, I'm going to have a negative 3 times an x squared times an x cubed. This is what I mean when I'm multiplying my largest exponents on each one. When I multiply these two together, I'm going to get an x to the 5th. So this one has degree 5. Okay? So basically, it's, this times this exponent right here, times this, so that's going to be an x squared. This exponent times this is x cubed, and then multiply these together. X squared times x cubed gives you 5, x to the 5th. Okay. Now let's find the zeros. This thing is multiplied, all factored for us. So to find the zeros, essentially what we're doing is negative 3 times x plus 1/2 squared times x minus 4 cubed equal to 0. And then you said each of these factors equal to 0. Well, from this one, if I set x plus 1/2 equal to 0 and solve that, I get x equals negative 1/2. And technically, I got this answer twice because I could have rewritten this as x plus 1/2 times x plus 1/2. So this one has multiplicity of 2. Since 2 is an even number, I touch, but do not cross at this x-intercept. Now from this one, I get x minus 4 equal to 0, which means x equals 4. So 4 is one of my x-intercepts. Now how many times did I get this? I got it 3 times. So this one has multiplicity of 3. And since this is an odd number, I'm going to cross the x-axis at that point. Okay? So if it's in factored form, you just figure out all your zeros, and then your exponent tells you your multiplicity. Okay, now we talked about turning points, and I said that we're going to be able to find the maximum number of turning points. And whatever your degree is, the number of times you're allowed to turn around is at most 1 less than that. So if your degree is 5, then you can have at most 4 turning points. If your degree is 4, you can have at most 3 turning points. It's always 1 less. Now you don't have to use all of your turning points. So I could have something of degree 5 and not have 4 turning points, okay? But that's the most you're allowed to have. And if you think back to when we were talking about x squared, we had at most 1 turning point, okay? Because, you know, if your degree was 2, you had at most 1, okay? And then a cubic could be something like this, where you have 1 turning point here and 1 turning point here, or it could be something as simple as that, where you have no turning points. Okay?